Hey, you alright there? What caused you to fall? I mean, sure, you could have tripped, but I mean, after that initial force of velocity, you're still accelerating towards the ground. So, what causes that? Oh, hey there. So, apparently there's a force that pulls us to the ground and keeps us from flying off into the depths of space. It's called gravity. Now, there are many theories explaining gravity, why it works and how it works, but one of the better theories is Einstein's theory of general relativity.
You see, Einstein figured that space and time are so interconnected that they can be treated as one thing. He dubbed this space-time. An easy way to visualize space-time is as a two-dimensional grid throughout the universe. And get this, space-time can be distorted or curved by mass. This curve created by mass in space-time is what we call gravity. We've known for a long time that the more massive the object, the stronger its gravitational pull. In physics, objects travel in the straightest path, or the path of least resistance. So in deep space, for example, where there are no bodies exerting the force of gravity on any objects, the path of least resistance would be a straight line. However, in the presence of gravity or curved space-time, that straight line would instead become a curve, traveling along the path of least resistance. Now, remember when I mentioned that larger masses create a stronger gravitational field? If we were to visualize spacetime as a 2D plane, stronger gravitational fields would create a deeper or lower depression in that plane. According to Newtonian physics, these depressions in spacetime are called gravitational potential, with higher gravitational potential meaning weaker gravity fields, and lower meaning stronger fields.
Now, you see, general relativity uses something called metric tensors, but that's for another time. General relativity also states that differences in gravitational potential can cause a variety of really cool effects.
One of those cool effects would be gravitational redshifts and blueshifts. Gravitational redshifts are caused when light travels from a lower gravitational potential, a stronger field, to a higher one, a weaker field, and loses energy. See that light? You still lose something! Light can't go slower than the speed of light, for it's a constant of the universe. So instead of losing energy by losing speed, light loses energy by going to a lower frequency on the electromagnetic spectrum, and becomes a redder color. Blueshifts are the opposite. When light travels from a higher gravitational potential to a lower one, the light gains energy and the frequency increases on the electromagnetic spectrum, and becomes a bluer color. Redshifts and blueshifts aren't the only cool way light can be affected by gravity. According to general relativity, when light travels from a source behind a gravitational field, light bends around the object, creating a distorted image of the source. This effect is called gravitational lensing. This is Hemzel. He somehow produces light. His position is directly behind a black hole and far away relative to us. Normally, we can't really see him that well, but when the light he produces travels towards the black hole and bends around it, what we see in the end is a brighter but distorted image of him in the shape of a ring around the black hole. This particular effect is called an Einstein Ring. Gravitational lensing is such a useful thing because it allows us to peer farther into the universe, because it acts kind of like a magnifying glass, enlarging images of objects light years away. Time dilation in general relativity is different from time dilation in special relativity. In special relativity, the faster you travel, the slower you would experience time relative to others who are not moving. In general relativity, because space-time in its entirety is distorted by gravity, time can slow down near gravitational fields. This effect is called gravitational time dilation. The lower the gravitational potential, and the closer you are to the center of gravitational potential, the more time dilates or slows down relative to someone who's in deep space. Fun fact, because of gravitational time dilation, the core of the Earth is calculated to be 2.5 years younger than the crust due to it being nearest to its center of gravitational potential. If you had a friend who traveled up into a motionless space station away from gravitational fields, so relativistic time dilation does not counteract the effects of our relative gravitational time dilation, time would pass faster for him relative to us, and time for us would pass slower relative to him. For both him and us, it would feel as if time were passing normally. However, if he were to return to Earth, he would have aged a whole lot more compared to us.
General relativity is such a great breakthrough in science because one man was able to predict so much about the universe even though he had no previous observations before it. This gives us hope that one day humankind will push through the boundaries of science and go farther than we ever thought to go before.